A tipping point that scientists didn't even know about may have just been crossed in Antarctica. I'm not sure if I can communicate how important this change is, but stay with me because I'm gonna try. After we began observing the Earth from space in the 1970s, researchers noticed something strange. In the Arctic, sea ice declined just like you'd expect on a warming planet. Scary, but predictable. But in Antarctica, the sea ice was growing. The pattern held for decades, but then around 2015, everything changed. Antarctic sea ice suddenly fell off a cliff, leaving scientists dumbfounded.
In a matter of months, we saw a massive decline, roughly 1 to 2 times the size of Greenland.
This fast of a trend reversal is extremely rare in nature, especially at this scale. Then it happened again.
It got to 7 standard deviations. At that point, it's just dumb, right? If you do the numbers, it's 1 in 700 billion.
So now the question becomes, is this change permanent? This matters because Antarctic sea ice helps drive the planet's overturning circulation, including the AMOC, which is the planet's largest heat transfer system, and it regulates global weather. Massive loss of sea ice will slow this system down, speed up sea level rise, and warm the planet far faster than currently predicted. And to understand if this is permanent, first we need to understand why it crashed and why it was even growing in the first place. Let's find out. Before we go any further, I just want to thank everyone who's joined our Patreon or purchased merch. Your support really helps us, so please click the link in the description and join us. Bottom water formation has to be one of the least interesting scientific terms ever invented, but it is also one of the most important for understanding this story and quite literally the fate of the planet. So here it goes. Around Antarctica in the Southern Ocean, when seawater freezes into sea ice, most of the salt gets left behind in the surrounding ocean water.
Extra salty brine is actually rejected from the bottom of the sea ice when the sea ice is freezing. And this really dense, heavy water, it circulates around the shelf around Antarctica, and some of it sinks into the deep ocean, and it forms this deep ocean circulation. And this is really important for the global ocean circulation, how the oceans distribute oxygen and nutrients and uptake heat and carbon. And so sea ice is important in this ocean functioning, which is also important for our global climate.
And then there's sea level rise, which sea ice protects against in 2 major ways. The first is something called the albedo effect, or how much sunlight a surface reflects back into space. Bright sea ice acts like a mirror, reflecting a lot of the incoming solar energy. Dark ocean water absorbs much more of that energy. On the other side of the world, near the North Pole, Arctic sea ice has been declining for decades, meaning it has less albedo or reflectivity. As a result, the Arctic is warming 4 times faster than the global average. 4 times. That's incredibly significant. This extreme warming is called Arctic amplification, and we haven't seen nearly as much of this amplification around the South Pole yet. If these recent losses in sea ice around the South Pole are in fact the new normal and begin to look anything like it has at the North Pole, this is going to change. And extreme disproportionate warming at the South Pole is especially bad because that's where the vast majority of Earth's ice sheets and sea level rise potential lie. The second way sea ice protects against sea level rise is by acting as a buffer for Antarctica's ice shelves.
It physically protects the Antarctic coast and the ice shelves. So when waves travel through sea ice, they're damped. And this means that they can't impart their energy on the ice shelves. But when sea ice is absent, waves, they break on the ice shelves, and they can break up the ice shelves faster than they otherwise would. Once we have these ice shelves collapsing, this means that the Antarctic ice sheet, the ice that sits on the continent, can slide into the oceans faster, and this will raise global sea levels.
So for all of these reasons, it was great news when Antarctic sea ice hit a record high in 2015, even as the world and the Southern Ocean grew warmer.
Then all of a sudden, in a matter of months, we saw a massive decline, roughly 1 to 2 times the size of Greenland. So it's a very large change in the sea ice coverage, completely unexpected. There was a discussion about what if the satellite data are for some reason not correct.
The sea ice remained low through the next few years before slightly rebounding in 2020 and 2021.
We thought, okay, maybe there was kind of an extreme event, and then things are going back to normal. But instead, around 2022, we saw another big decline.
This collapse was catastrophic for the emperor penguin population. The sea ice broke up in 2022 before the babies were ready to swim. Nearly 10,000 died, leading to the species to be listed as threatened. So why did the ice grow in the first place? And why the sudden crash? Well, a decade after the first crash, scientists think they have an answer. Ocean water is usually layered or stratified in a pretty intuitive way. The sun warms the surface and colder, denser water sits below. But around the poles, that layering flips because the extremely cold air freezes the surface while the water underneath remains warmer and closer to the ocean's average temperature. This layering is only possible because the surface water is less salty than the warmer water underneath.
We've been observing that this two-layer system strengthened for decades. So we had colder and fresher surface waters and warming at depth. In that sort of scenario, these two layers tend to be kind of separated, and therefore the heat that is stored at depth cannot really reach the surface where there is ice.
During this stable two-layer era, the prevailing winds around Antarctica, called the westerlies, strengthened as well. These winds pushed Antarctica's coldest surface water northward into the open ocean, which promoted sea ice formation. And as the fresh water cap blocked heat from the warm water below, sea ice reached a record high. Then in 2016, the rising water temperature below the surface finally combined with changing wind patterns and ocean currents to mix the deeper, warmer salt water with the colder surface water.
So similar to the sea ice decline, we see an increase in salinity at the surface of the ocean.
Meaning the cold freshwater cap was disrupted, preventing ice formation, which allowed more solar heating of the surface water, which melted more ice, which allowed still more solar heating. This feedback loop led to such a dramatic loss of sea ice in 2023 that it appeared to be statistically impossible.
It got to 7 standard deviations. At that point, it's just dumb, right? If you do the numbers, it's 1 in 700 billion.
Now that scientists had a good idea of what caused this feedback loop, the question became, was this just an incredible anomaly or something more fundamental and long-lasting? Ed and his team turned to a large computer model to find out.
We ran it from about the 1950s through to the modern day, just a couple of years ago. And we looked at the relationship between summer sea ice and ocean temperature. And then what we did is we imposed a massive loss of ice on that to mimic the 2017 record low summer.
And that's when things began to click. When you force an extreme summer ice loss, the model shows the ocean holding on to extra heat, so the following winter, sea ice has a harder time bouncing back. This creates a compounding effect from one year to the next. And that persistence very likely explains the second extreme drop in 2022.
So it has gone low and it has stayed ridiculously low, which, I mean, 4 years in, it's kind of hard to say it's a blip, right? This looks like the change is here to stay.
So all signs point to this extreme drop of sea ice being a tipping point for Antarctica. Now that it's been triggered, researchers believe that the change is likely permanent.
The response to an extreme loss of sea ice is not just the normal response made a bit bigger, but it is structurally different.
Once you put heat into the ocean, it's really difficult to get that heat out. The ocean holds onto it, and the ocean is going to continue to take up heat. And so because of that, our understanding of that process and that mechanism, I don't see a way that the Antarctic sea ice is going to bounce back from that.
The Southern Ocean has likely tipped into a feedback loop of warming that will continue for centuries. So what does that mean for us and the natural world? Well, it probably means we will lose most emperor penguins. And as we mentioned earlier, it also means a slowdown in our planet's circulatory system, including the AMOC, which is the ocean's largest heat transfer system, and its sibling, the Antarctic overturning circulation, which models suggest could slow by around 40% as soon as 2050. And as Ariane mentioned earlier, sea ice protects Antarctica's ice shelves from waves, which slowly chip away at them, leading to faster sea level rise.
So that's bad news. But it's really bad because we don't actually incorporate that effect in our climate models that we use to predict sea level rise. So we're almost certainly under-predicting how fast sea levels will rise using these models because we're not accounting for that impact. There have been multiple studies coming out in the last few years suggesting that we have already passed, or we are super, super close to the points of no return for multiple different bits of the Antarctic ice sheet. So then the question becomes, how quickly is it going to melt?
And this question, as well as methods to adapt, are what researchers are currently studying, which is why funding for scientific research is crucial, because the choices we make now still matter. They can slow the pace of change and buy us time to adapt.
Climate doomerism is already a problem. That's like saying, oh, well, I've injured my arm, so I might as well just chop it off, right? That's not helpful, because we know that the more we warm, the faster these things come. The more sea level rise there will be, the faster ecosystems will collapse. But the converse of that is that we can warm less quickly. We can slow it down. We can have sea level rise that happens more slowly. We can have ecosystems collapsing more slowly. And that gives us time to save them. And that's really important.
I want to give a huge thank you to our Cat 5 Patreon members right here. If you want to go deeper, we've got extra interviews and behind the scenes on our Patreon. And if you found this video helpful, like, subscribe, and let us know what questions you want us to chase next. We'll see you next time.